Hello, I'm Claire Gilliam, and this is my lab number 2, presentation on charge tape revisited. So first we have our introduction and physics principles. So, what is this lab's purpose? Well, we wanted to observe and determine the charges and forces acting on a piece of tape, and then compare our observations from the first experiment with the computational model we made. The tools we used were scotch tape as our charged object and glow script to create our computational model. The physics principles we used were Newton's second law to calculate the charge and the forces acting on the tape, gravitational force equation to calculate the force of gravity on the tape, and Coulomb's law equation to calculate the electric force on the tape. The results were we found our line and point charge findings differed, and that our line charge is more accurate than our point charge as it factors in superposition and the change in electric field along the tape. Modeling the experiment, we see that we assume the charge is equally distributed along both tapes. Each U-tape has the same amount of charge, and the air resistance can be ignored. In defining the system, we see that the system is just the U-tape and the bottom tape, or the top tape and the bottom tape, and the surroundings are everything else. Our free body diagram shows that for tape B, the electric force is pointing up because it is repelling against force A, and this is in the opposite direction to the force of gravity, and that's what creates a net force of 0 as they equal each other, but they are in opposite directions. So we have our experiment and observations. So first we measured the length of the tape is 0.2 meters, width is 0.02 meters, and the mass of the tape is 10 times negative 4, 2 times 10 to the negative 4 kilograms. And our final condition was that it took a distance of 4 times 10 to the negative 2 meters to get between tape A and B to get tape B to float. The procedure was we stuck both tape A and tape B to a bottom tape that was stuck to the table to create a charge on both pieces of tape. We suspended tape B on two objects and held tape A up to the bottom of tape B and measured the distance between them to find where tape B floats. And the charged piece of tape, once it was charged, looked like this. And it was attracted to our hands as our hands are positively charged. So, calculating the force of gravity, we find that the force of gravity is equal to 0.001962 newtons. We knew that this was equal to the electric force because the net force is 0, and then using this we solve for Q, which we found is 1.866 times 10 to the negative 8 coulombs. Then we were able to find this, use this value to calculate the electron deficiency, which is 1.166 times 10 to the 11th. Then we found the number of atoms on the tape per surface area, which is 4 times 10 to the 17th. And then we use this to calculate the number of deficient atoms per number of electrons along the whole piece of tape. And we found there is 1 deficient electron for every 3.29 times 10 to the 6 atoms. Next, we have our computational model. So, we initially set our constants. K is equal to 9 times 10 to the negative 9, 10 to the 9th. G is 9.81. The charge of the proton and electron is 1.6 times 10 to the negative 19th. And we inputted our distance between the tapes as D, and the mass as 0.002. And originally, we put Q in as 1.866 times 10 to the negative 8th from our previous experiment of the charge of the tape. However, multiplying by 1.755 is what actually allowed the force of the gravitation and the electric force to equal each other. Then we created a function which took in the parameters of the charged particle and observational location position to then calculate the electric field at the tape. Then we had to create the actual line of tape for tapes for both pieces of tape. And then we set the position of the top tape as D, representing our experiment as the distance was D to get it to float. And then N just equals 100, so we have a more accurate depiction of the experiment. So our E scale, or our electric force scale, was 0.000001. Our electric force and gravitational force scale is 50, which we multiply for both fields, and then lines 114 to 129 represent superposition as we change the electric field equations depending on where you are along the piece of tape, which more accurately represents the charge on the piece of tape. And then we were able to create the arrows representing each force on the piece of tape, whether that was gravitation or the electric force. Our final conditions were that the electric force and gravitational force are both equal to 1.96236 times 10 to the negative 3 newtons, and there are possible errors such that the charge is not actually equally distributed along the tape. Air resistance we did ignore, and there might be other net forces. So discussion and conclusion. So what if we modeled the tape using a point charge? Well, we found that between Lab 1 and Lab 2, where we modeled it with a point charge and line charge, there is an actual 175.5% difference between the charges in Lab 1 and 2, which shows that modeling them using different models leads to different results. And why is this? Why do the estimates differ? What is the difference between a point and line charge model? Well, when we use the point charge model, we're just considering one particle. However, with a line charge model, we consider it superposition, so how the charge actually changes depending on where you are along the tape, which creates a more accurate model, as that is how it is in real life. Thank you.